these were the two rational functions that we called sort of parent functions in Wednesday's class, and we only have two choices here. One of these is the reciprocal function, and the other one is 1 over x squared. So if we were to label each graph with its formula, this is the reciprocal function. It has symmetry about the origin, okay? And this is the other function, 1 over x squared. And we spent some time looking at different transformations of those in the class activities on Wednesday. So one of the big ideas that came up on Wednesday was this idea of a vertical asymptote. And in each of these graphs here, the vertical line going right through the origin is acting as our vertical asymptote, because we find our vertical asymptotes by finding the values of x that make the denominator 0. So in this case, it was x equals 0 for both of them. Then here are three equations, and I'm asking you to give me the equation of the vertical asymptotes. So if you look at this equation, there's no vertical asymptote. So this one has none. In this equation, we have one vertical line that our graph approaches and goes towards positive or negative infinity, and it goes straight through x equals 2, and voila, that is its graph, x equals 2 for the vertical asymptote. The next graph has two vertical asymptotes with a lot going on either side of them. The two vertical asymptotes here are x equals positive 2 and x equals negative 2. So whenever I ask you for an equation, that's what I expect to see, is an equation. Can the graph of a rational function intersect a vertical asymptote? Never. And how do we indicate a vertical asymptote on the graph? With a dotted line, dotted vertical line. Okay, so that was what we did on Wednesday. So let's take a look at today's material. So today we're going to use some similar ideas, but we're going to expand the sort of the body of rational functions we can look at. We were limited on Wednesday to just functions that were transformations of these two. Now we want to be able to look at any rational function and know how to graph it. And again, we're looking for sketches. We're not asking for accuracy and putting in individual points. So we've got to go a little bit more to like the overview above the trees rather than how many leaves are on each branch kind of thing. Okay, so here's a rational function. So what values are excluded from the domain of f of x? What values are excluded? What value or values are excluded from the domain? So if I asked you for the domain of this function, what would you tell me is the domain of that function? Everything but negative 3, okay? Your excluded value is not the domain. The domain is a set of numbers that you can plug into that function and get a number out. It has meaning. It can be defined. So when you talk about the excluded value, so the domain here is the set of all x except negative 3. And the person that was answering the question answered it correctly. The first question said, what x value or values are excluded from the domain? X equals negative 3 is the excluded value. So excluded value is x cannot be negative 3. Because if you put a negative 3 in there, you're in deep trouble because you have 0 in the denominator. Okay. So that might lead you to think that you automatically go to your graph and put a vertical line straight down through x equals negative 3. Because that's what we were talking about on Wednesday. But there's a little situation that makes that different, and we're going to examine that right now. So if we look at this function, we notice it can be reduced further. And to reduce any kind of fraction, you know you have to factor it. So if I factor the numerator is the difference between two perfect squares, which means I can always factor it into two factors that are called conjugates of each other. That means They look almost the same except for their operations are opposite or inverse, addition and subtraction. And then you notice that your denominator looks exactly like one of the factors in the numerator. And you can cancel them out to 1. And notice what you end up with, x minus 3. Well, x minus 3 is sitting over 1, so there's nothing in that denominator that's going to cause you any problem. However, don't forget, this comes from this fraction, so x still can't be negative 3. Okay, even though you could put negative 3 in here, it's not part of the domain. So what do you do with that? Well, this is what you do with it. You look at this complicated function, and it now becomes x minus 3, which is just a straight line, x minus 3. What's x minus 3 look like? Well, it goes through 0, negative 3. So if I asked you to graph this line before you came into class, you'd say, okay, 0, negative 3 is my y-intercept. My slope is 1. My x-intercept is positive 3. And you would just draw a straight line right through there, right, with slope of 1. So let's see if I can do that and try to get it to be fairly accurate. So let's see. I'm going to draw a straight line. Oh, I missed it. Maybe I just better do it by hand because this is tough. Come on, cut. There we go. All right. So straight line. To the right one, up one, right one, up one, right one, up one, right one, up one, right one, up one. Okay, so I've got some points there. And let's see. Down one to the left one, down one to the left one, down one to the, uh-oh, I'm in trouble. Look where I am. Where am I? What's my x value right here? Negative 3. I can't be negative 3 because my original function wasn't defined at negative 3. So what the heck am I going to put right there? Huh? No. The whole, right, the whole. Remember we had a whole on Wednesday in our graph? So this thing looks just like the straight line that goes through 0, negative 3, and 3, 0 with a slope of 1. Exactly like the straight line with one little teeny exception. It has a hole at x equals negative 3. No, there's no vertical asymptote here. That's what makes this function different than the others, because when you reduced it, it became linear. And look, if it really was y equals x minus 3, you could put negative 3 in here. And you see, that's how you get your y coordinate for that point right there, because that point is negative 3, negative 6. It's just instead of making it solid like it's part of your function, you have to put a open circle because negative 3 is not allowed into your original function. So it's kind of strange, but that's how you get the whole in your rational functions, is when you find a common factor. You can find more than one common factor, but usually you have at least one common factor, top and bottom. You're going to have one whole in your graph. Now, as you saw on Wednesday, let's go quickly back to Wednesday's opening slide. So here's a rational function. So it didn't end up looking like a straight line. It ends up looking like the reciprocal function shifted right 1 unit. That's what it looks like. But it has a hole at what value? X equals 2. So we now can kind of come up with what we think might be the equation of this graph. We can work backwards. So if it has a hole at x equals 2, then we work backwards to the factor. Working backwards to the factor is setting it equal to 0, because a factor is where an x value that makes it 0. So what factor would make that 0? Well, you subtract 2 from both sides, x minus 2. So if there's a hole at x equals 2, that means the factor is x minus 2, because if you put a 2 in there, you get a 0. Normally with polynomial functions, that's not a problem. It's just where you cross the x-axis. But with these rational functions, this is where your denominator is 0. But not only is your denominator 0, it's a common factor, so guess what? It also appears in your numerator. What other value makes the denominator 0? That's where your vertical asymptote comes in at 1. So that means you have another factor in the denominator. So this is one possible equation for f. See, that's a possible equation for this function. If I gave you something like this, you'd say, ooh, I have a common factor top and bottom, so I can reduce this to become 1 over x minus 1. And now it looks like something you would have graphed on Wednesday. You would have said, if I cover up this minus 1, it's the reciprocal function shifted to the right 1 unit. So if it started off looking like this, 1 divided by x minus 1, it would look just like this graph without the hole there. But because it had that common factor top and bottom, at 2, it has a little baby hole. Because 2 is not part of this domain, just like 1 isn't part of the domain. So if you look at your denominator, you can't automatically assume that the value of x that makes your denominator 0 is a vertical asymptote, right? That's where we were on Wednesday. If the value that makes your denominator 0 also makes your numerator 0, then it's a common factor and you can reduce. That's where you'll have a hole in your graph, not a vertical asymptote. So you can't automatically go boom, boom like this and, you're all done. You have to think about, now if the top said x plus 4, then I would have 2 vertical asymptotes because it'd be no common factor. So that's a little bit of a change from what we did on Wednesday. How do you get those holes? So now when I go to graph this, I graph what the reduced equation looks like, which in this case is a straight line, and at x equals -3, I would evaluate this as if it was just a straight line, and instead of putting a solid dot right there at -3, -6, I put my hole. Okay. So that's one little change from Wednesday. Any questions on that before I move along? All right, so the next thing we have to kind of get a hold of is this idea of a horizontal asymptote. Now, all of the horizontal asymptotes we looked at on Wednesday was the x-axis. Our graph, when we went out to positive and negative infinity, got really close to the x-axis, which means its output was getting really close to 0. It was getting smaller and smaller. Well, there are other times where your horizontal asymptote may be a value different than 0. So let's take a look at this first one. If you look at these 3 rational functions, they all look very similar, but each one has a little change from the previous one. So let's take a look at the graph, and then let's put in the symbolic notation for what the graph is saying for the end behavior. And then we'll go back and try to figure out, is there a way to get the horizontal asymptote without plugging in numbers and seeing where the value approaches? So as x goes to positive infinity, so I'm on the right side of my graph and x is getting huge, or as Bernie Sanders says, what does he say? Huge. So as x gets huge in the positive direction, what's happening to the value of my function? What's it getting close to? 3, right? The output of 3. As x gets really, really small in the negative direction, what's the value of my function in the end? What's it getting close to? 3. Okay. So notice here, your horizontal asymptote way out here in the end is -3. You see really close right here, look, really close to the y-axis, you're way down here at like 1 and 1.5 and 2, you're approaching it. So often when I draw these rational functions, I only put the horizontal asymptote in the ends, because I know that's where I'm going, that's what I'm moving towards, Those are my goals. Being 3 is my goal. And as I go out in the positive and negative direction. So if I were doing this symbolically, I would say as x gets really, really big, moves towards positive infinity, the value of my function approaches 3. And as x moves towards negative infinity, it also approaches 3. And that's what that graph shows me. The next graph is more what we're used to looking at, like our graphs look like in Wednesday's section. As x gets really big, it's approaching 0, which is our x-axis in both of these situations here, as x gets really, really big and as x gets really, really small. So that's kind of what we were used to seeing. So here our horizontal asymptote is the equation y equals 0. And here our horizontal asymptote was the equation y equals 3. And the next picture, do I have a number that the graph's approaching as I get really big or really small? One single number? No, they're both going, as I go to the right, my graph's rising without bound, so it's approaching positive infinity. I haven't quite figured out why this new pin does that. So positive infinity and negative infinity. Okay. So your question is, right now, is there a way without the graph? We had the graph as a visual aid here to help us determine the horizontal asymptote. Is there a way of looking at your function, the equation of your function, looking at this function f here and coming up with the number 3? Look at your leading coefficients, 9 divided by 3. But every single one of these has leading coefficients 9 divided by 3. Well, in one case, in this first case, it certainly works out that if you simply divide 9 by 3, you get your vertical asymptote. Geez, wouldn't that be great if that's all you had to do? But look, in this next one, you got a 9 in the top and a 3 in the bottom, but your horizontal asymptote. Your horizontal asymptote isn't 3. And here you have a 9 and a 3, but you don't even have a horizontal asymptote. So Jasper zeroed in on part of the answer. But we have to figure out, when do we just get to take the leading coefficient in the top, which in this case is 9, and the leading coefficient in the denominator, which is 3, when do we get to divide them? Liam? To an even, what's to an even power? Oh. Similar powers. Okay, I need something a little stronger. Okay. All right. Well, we got a lot going on. So Liam was talking about even degrees, but yeah, Liam, if I had a 4 up here and a 2 down here, it wouldn't work, or vice versa. So think about this for one little minute. I could put it into a calculator, but just think about it for a minute. What are we trying to capture? We're trying to capture if this function approaches a single number when x is really, really big or really, really small. So look at this first function. If you put 1,000 in for x, 1,000, well, 1,000 squared is what? 1,000,000. So what would our numerator be? 9 million. What would our denominator be? 3 million plus 1. How big is that 1? If I was going to give you $3 million, would you care about that $1 extra? Oh, come on. You could donate it to a campaign. Come on. You can tell they're in business. All right. So how much impact does that single constant have when x is really big, or even if x was negative 1,000, you're still going to get the same thing, 9 million over 3 million in 1. How much impact does it have? Not much at all. It's totally insignificant. So you can literally cover that up because your numerator and denominator, they're both growing sort of at the same rate because they're both being squared. And if you completely take that plus 1 out, what would that reduce to? 9x squared divided by 3x squared. 3, because your x squares become 1. So it's just 9 divided by 3, which is 3.
So does that apply to C then?
Hang on, we're on number A. All right. So what's different about A than B and C? The degree of your numerator and the degree of your denominator is what? Not similar. We can even be more. They're exactly equal, the same, right? So that's part 2 down here. That goes with graph A. Right here, this is graph A. If the degree of your numerator equals the degree of your denominator, then your horizontal asymptote is just the division, the ratio of the leading coefficient on top and the leading coefficient on bottom. Oh, that's good. So if I look at my, and it doesn't even matter whether I had on the bottom there 3x squared plus 2x plus 1. It doesn't matter how many terms are after it. They all, when you get really, really big values of x and really, really small values of x towards negative infinity, they just have no significance at all. All right, now the next one is a little bit different because the degree in the numerator is only 1, 9x to the first, and the degree in the denominator is 2. So if x was 1,000,000 now, I'd have 9,000,000 over 1,000,000 squared times 3. So I'd have this really huge number in the denominator. And as my denominator gets big, 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 my fraction, the value of my fraction gets teenier and teenier and teenier. It goes towards 0. So whenever the degree of your numerator is smaller than the degree of your denominator, then that's A. That's this first one. That's the graph B. You're always going to approach your x-axis. Always. So your function approaches 0. All right, and then finally, in this last one, notice the degree in your numerator is bigger than the degree in your denominator. When that happens, you have no vertical asymptote. So that's C. All right, so you'll get a chance to practice that with all of your class activities. But to convince yourself, you should just, take out your calculator and put in some really big positive numbers and some really small negative numbers like negative 1,000,000. And you can watch this thing, or you can just put it into your graphing calculator as an equation and just put in values in your table, and you can see how this works. But the graph also shows you what your table on your calculator would show you. So fun, question mark? I guess fun is, in the eye of the beholder. Fun facts about horizontal and vertical asymptotes. You can have several vertical asymptotes, but you can only have one horizontal asymptote. And even though you could never intersect a vertical asymptote, you could intersect and cross a horizontal asymptote. That's possible. Here are all the steps to graphing a rational function, and instead of reading them to you, this is what you'll be referring to in your class activities. So I want to take you through a couple graphs, and then I want to have you spend the time trying them on your own. All right, so here's a graph. All right, so where do you start? Well, it's probably a good idea to check out some different ideas. What does it say in your steps? Make sure your function's reduced. Why do we care about the function being reduced? What information does that tell us if we can reduce it? Yeah, your overall function could be easier to graph. That's true. And if I can reduce it, beside getting us maybe a function that's easier to graph, what other information would that give us if I could reduce it? Huh? We would have common factors, and what would that tell us? A whole, right? So the reason why you want to see if you can reduce it any further is not only does it give you important information like Jasper is referring to, if we factor that denominator, it's going to tell us possibly where our vertical asymptote is, or a whole. Now the whole is only going to happen if you have a common factor top and bottom. So if you take a look at this first fraction, There's no common factor of x in the bottom or an x squared. So this isn't going to have any holes, but when you factor that denominator, it's certainly going to help you with the excluded values, the values that make your denominator 0, which makes you very unhappy. Happens at -3 and +3. Now I've put these little toolkits at your table. You may want to take some colored pencils out because color will help you today. So our vertical asymptotes are x equals 3 and x equals -3. Those are the equations. All right. Well, what else is going on here? Well, you want to see if you have any x-intercepts. Well, let's see. What's an x-intercept? Oh, yeah, that's where my output, f of x, is 0. So to find your x-intercept, all you ever have to do is just think about what an x-intercept looks like. Your output is always 0, and you're trying to find the x value that makes that 0. So you set your function equal to 0 to find that. Let's be careful for a minute. Let's look at that. When does that function equal 0? When x is 0. Why? Because you don't have to pay any attention to the denominator. The only time a fraction is 0 is when your numerator is 0. So 2x squared equals 0 when x is 0. So our x-intercept here is 0, and it's also our y-intercept. So there we go. So if you were walking along this x-axis from -infinity, and you're coming in, and I'm just moving my hand along here, where's the first sort of barrier I bump into? -3. So I want to think about how is my real number line being sort of parceled up? How is it being kind of chunked up? So I could sort of think of this real number line here, or my domain, being in parts. I can think of it as coming from -infinity up to -3. And I bump into that vertical line. And then I can take a step to the right of that vertical line, -3. And then where do I bump up to against something again? Right at the origin, that's my x-intercept. So I could go from -3 to 0. Would be another little chunk of my domain. Notice I have parentheses here because these are places, at least here I can put bracket because you can have x equals 0, but here I can't have x equal -3. And then I take a little step on the other side of that. The other side is 0, and I'm kind of moving along until I bump into 3 again. Oh, okay. No, this is, remember, this is an interval here, Ramses. So interval are over the x values. It's not a point. I would just have my bracket at 0 because x can't be 3 or -3. It's not allowed. So that's why I have to have the parentheses there. Okay.
Can you unionize all that?
I don't need to union it. I would union it if I was asking you what the domain was. Then it would be all of these chunks put together. Yeah, that's when I would do the union. Okay, and then finally, hey, look, freedom's happening because once I take a step to the right of 3, I'm good forever and ever. 3, infinity. So notice I have 4 colors. And this is just my way to help you think about that's sort of where you want to focus. You just want to focus on each part of this x-axis and think about what is my graph doing on each segment here? What's happening to it? And as you know, when you get close to -3 from either direction, and when you get close to this other vertical asymptote at x equals 3 from either direction, it's like Saturday night at UMass. You go crazy. okay? Your behavior goes nuts. You're either going to go to positive infinity or negative infinity when you get close to it. The question is, am I close to it above the x-axis and shooting up, or am I below the x-axis and shooting down? Now, when you're above the x-axis, the value of your output, the value of your fraction is positive. When you're below the x-axis, the value of your fraction is negative. So all you have to think about is the value in this region. Think of these as 4 different regions. You've got your pink region right here, which is from negative infinity to negative 3. You've got your purple region, which is from negative 3 to your x-intercept 0. You've got your blue region, which is from 0 to positive 3. And then finally, you've got your green region. You got 4 regions here. That's all you have to do is focus on those. Nick?
If you're including 0 in multiples there, why separate them into 2 separate ones? Why not just have one?
Because the graph can change sign at the x-intercept, as we know. If you go back to your polynomials, if you are even multiplicity, you don't change sign. But if you're an odd multiplicity, you change sign at your x-intercept.
For this one specifically,
we don't know that until we do the next couple tests. Okay, so let's not get too far ahead. All right, so you've got this all chunked out into your regions, you're ready to go, but you still have to answer the question, what happens in the extremes way out here? What's my horizontal asymptote? So let's go back and look. We've got our vertical asymptote. Let's throw in our horizontal asymptote. We look at our original function, and if it's in factored form, you have to at least know what the degree of the denominator is. You either got to, in your head, multiply that out and know that you get x squared, or you say there's a 1 on that factor and a 1 on that factor, so my degree would be 2. So you go back and you say, okay, the degree of my numerator and denominator is the same. You say, whoopee, because you can take everything out to the right of that, and you know that that would reduce to 2 divided by 1. So your horizontal asymptote is the equation y equals 2. So that means way out here in my extreme, my value of my function is going to be approaching -2 way out here. All right. The degree of, it's all written down for you there, just in case you forget, Jasper, in the conclusions. But because these are sort of growing at the same rate, just like we did with the money, this little -9 here is going to have very little effect on the value. So think about putting a large number in there like 1,000 again. It would be 2 million divided by 1 million. So it gets really close to 2 divided by 1, which is 2. Okay. All right. So let's see. Equals. All right. Yep. Just the leading coefficients when the degree of the top and bottom is the same. You don't have to worry about anything else. All right, so now look at this. What are some possibilities? All right, I'm hugging this line. Watch my hand. I'm hugging this line. And as I get close to -3, boom. Or remember, way out here, you're hugging the line. Look, you're hugging the line, you're hugging the line. And then you go, boom. Is that possible? Is it possible for me to go way out here at -1 million to be hugging this line? Is it possible for me to be hugging that line and then come down like that? Yeah, I'm asking you, can I do that with this one? We have dissension in the classroom. This is an impossibility because you have only one x-intercept and it's located at 0, 0. So there's no way I can be hugging the line y equals 2 for a long time and then have it go down into crossing the x-axis here and going down to negative infinity. What did you say, Jasper? It can drop down to 0, 0, but we've got to be on the other side of this line. Okay, Nick?
Just to clarify, anytime you're trying to find like equation equals 0 and it's a division problem, all you really have to look at is.
That's right. That's for your x-intercept. So with all of these rational functions, to find your x-intercept, ignore the denominator. Just look at your numerator. That's all you have to do. All right, so look, I've already answered that question. There I am. That's the first part of my graph. Now you say, I'm never going to remember that. Can't you just give me some steps, Kavanaugh, so I know whether I'm above the x-axis or in this case above this horizontal asymptote or below? Yeah, I can. And it's called the sign test. So all you have to do is pick a number in that region to the left of -3. It can be any number in the world. And remember, you're not interested in plotting a point. You're just saying, am I above the x-axis or below it? That's all. Am I a positive number or a negative? So pick an x value in that region from -infinity to -3. 64 billion, -64 billion. All right. So I have -64 billion. And I put it into this numerator. When I square -64 billion, I'm positive. That's all I need to know. And I double it, big deal. And then in the bottom, I square -64 billion, I'm still positive. And I don't care about the subtraction of 9 if I'm squaring 64 billion, right? So what's the value of my fraction? Positive over positive, which is positive. So that tells me I'm above the x-axis, and since this is my horizontal asymptote, I just start my curve really close. In fact, if I were graphing this, I'd probably even have it a little bit closer way out here. I probably would have it something like, I mean, again, it doesn't really matter as long as you have the gist, right? I'd probably have something like that. It just stays close and it zooms up. That's all. We don't really care about the details. Just the overall action. Molly? Yes. The sign test is to just help us with whether this curve right here is located above your x-axis. If it is, it means all your output is a positive number, or if it's below the x-axis. And it will never change sign within a region. So this axis here is this region goes from -infinity to my first vertical asymptote. So any number in that region will, when I plug it into my function, will either be a positive value or a negative. It will never change. Any number in that region. So instead of being silly and picking 64 billion, why don't we pick something that we can actually handle? -2 is not in this region. So let's pick -4. If you put -4 into your function, folks, again, you're only interested in the sign. I'll plug it in so you can see it, but you're only interested in the sign of the answer, not the actual value. Because all you want to do is know, do you start in the top or the bottom? Above the x-axis or below the x-axis. So look, -4 squared is 16, double 16, positive. I don't care what the number is. I'm not being snippy, I'm just saying the value, I'm not going to actually plot the point. -4 squared is 16, take away 9 is another positive number. When I divide a positive by a positive, my sign of the overall fraction is positive, so I just know I'm up here. That's all.
So as long as it's positive, that's how you can like
Right.
make sure
And
the
if
line test is correct.
yeah, and if my horizontal asymptote happen to be my x-axis instead of the line y equals 2, I would just be starting close here and zooming up. That's all. Yep.
So with the other side,
All right, so let's take a look between -3 and 0.
Can't go with the x squared.
I don't know what you mean by that.
Well, the x squared, anytime you have even exponential, like to square a negative number, you get a positive.
That's true, but it depends on, let's just see. Okay. All right. There's no shortcuts here, unfortunately. This is the shortest. There is a shortcut, but I don't want to tell you it yet because some people can't handle the shortcut. So I want to show you a very sort of structured step-by-step. Pick a number between -3 and 0, and let's not be ridiculous. -1, okay. It is fun to be ridiculous, I agree. When I put -1 in the top, am I a positive result or a negative? Now be careful. When I put a -1 down here, Ken, am I going to be positive just because it's a square? No, because when I put -1 in here, I do get a +1, but when I subtract 9 from it, what am I? Negative. The end result. Yeah, I don't know why this pen is doing this. It drives me nuts. So it's plus over minus, which is minus. So what does that tell me? Can we kind of calm down here, please? When I take a step on the other side of -3, instead of being way up here at positive infinity, I've changed my sign and I'm way down here at negative infinity. So now what am I heading for? Purple, I'm way down here. I'm heading up and I stop right there at my x-intercept. Because my x-intercept, I know I'm 0. So now the big question is, does my sign change and I go up towards positive infinity, or do I go down in region 3 to negative infinity? The only way I know is to do my sign test. So let's pick a number on the blue interval here between 0 and 3. What number do we want? 1. I get a positive in the top and a negative in the bottom. So my overall sign in that interval is negative. So that tells me shoot right down. Yes, it would be positive then. No, no. Then it wouldn't be right. Because there's no definition for dividing by 0. So they would have been in, right. Or it would have probably been a vertical asymptote. All right. Now pick a number, Ramsey, in your favorite region on your green line. 5. X equals 5. So is your top of your fraction positive or negative? And what's your bottom? So what's your overall fraction? Yep. So you start way up here and you hug that out to infinity.
My only question about that is,
Well, like, right. You were here Wednesday, yes? Okay. So on Wednesday, we talked about approaching this vertical asymptote from both directions. And when we get close to that, our value either goes up to positive infinity or negative. And because I know I'm positive from 3 to infinity, I start way up here. But I'm limited with the graph. I can't really start up like in the top of the ceiling, right? So I just know I'm really close to that. And I might come down and be, maybe more, have more of a curve there. I don't really know. I don't really care. I just want to try to capture the essence of the graph right there. And I know it's going to come down and it's going to approach this line. Now, maybe, Liam, it really would approach it like way, way out here like this, right? But again, I'm not trying to get an accurate. I'm just trying to sketch it. Okay? There's a lot going on with rational functions, folks. It takes all of the knowledge that you've been building really for several weeks and puts it all together. Other questions? Now, this is the part, if you don't understand what I'm saying, ignore me. This is how you can sort of not have to do all the sign tests. This is the shortcut. So if, I said there was a little one. Once you know that in this region your graph goes like this, to know when you take a step on the other side of your asymptote into the outer limits, whether you stay positive or change sign, look at the factor where x being -3 made your denominator 0. So here we are. That's the factor. What's the exponent on that factor, x plus 3? 1. Go back to polynomial thinking. When you had a multiplicity of 1, it's like a straight line. You go straight through your axes, right? When it was a 0 of the polynomial. Means you change sign. So if you look at that multiplicity, you know if you're positive on one side, you're going to be negative on the other. Look at -3. Has multiplicity 1. If you're negative on this side, when you jump over, you're going to be positive on the other.
So that was +9. But if this -9.
No, I'm just looking at this right here. That's all I'm looking at. Just the multiplicity.
Factor out the denominator.
Anytime you have an odd multiplicity on your factors in the denominator, you change sign at the asymptote.
If there was like, say it was, x plus 3 squared, you could still.
Then you would stay on the same side. If this was x plus 3 squared, instead of coming down here, I would be here and going like that because it's an even multiplicity. As I said,
You just simplify it to x plus 3, x plus 3, and then
no, it's still the same vertical asymptote. It's just your sign wouldn't change. Okay, folks, that idea is like a little bit more advanced. Just do your sign test. Forget what I'm trying to tell you. It's like 2 above there. It's just if you can handle that, great. But otherwise, just do your sign test. We're just trying to get quick sketches. You have 20 minutes, but let's just talk about this one real quick. Real quick. What's the horizontal asymptote? No, it's not 4. Because the degree in your numerator isn't the same as the degree in your denominator. If x is a really huge number, what's this approaching? 0. This is where you, and look, all you have to do, folks, is take out your calculator. Any calculator. You don't even need a graphing calculator or anything. Just take out a calculator. Put a really big number in there and look at what happens. 4 times a really big number, or really, here, 4 times -1,000 or 10,000 divided by -10,000 squared. .0004. That's pretty close to 0. That's what e to the -4 means. 4 times 10 to the -4. Anytime your denominator, the degree in your denominator is bigger, your horizontal asymptote is your x-axis. That's your horizontal asymptote. Where's your vertical asymptotes here? +1 and -1, because when you factor that, you get x plus 1, x minus 1. So you put these in. The degree of the numerator is smaller than the degree of your denominator. Your horizontal asymptote's the x-axis. It's all written down for you in the class notes. All right. What's our x-intercept? When is the numerator equal to 0? 4x equals 0 when x is 0. So to do your sign test, you've got 3 regions, folks. You've got this region. You've got this region. You've got this region. And you've got that region. So you have to do 4 sign tests to know what's happening to your graph. Okay? There's no way around it. If I asked you what the domain is and you didn't have to put it into these 4 intervals, I would just do this. That's what I would do for the domain. But if you did it in interval notation, then you can see how your actual graph gets chunked up here. So if you did this, so that would be that same domain in interval notation. Yeah, you can't do negative, oh yeah, for the domain, you're right, Spencer, you can do -1 to 1. I was just looking, which this is the same thing. I was thinking about, yeah, how you would have to chunk it out for graphing it, yeah. So that would be the domain if you put it in interval notation. So you've got quite a bit of time. get going on those rational functions. I gave you quite a few. You know the moral of the story.